In the next question, we have two balls that are being thrown from a 1 meter high step. Both have an initial velocity of 10 meters per second, but one is facing up and the other is facing down. In other words, two balls are being thrown 1 meter above the ground. Both have an initial velocity of 10 meters per second. One ball is being thrown up and the other is thrown down. 1. When will each ball hit the ground? And 2. What will be their velocities? Let's see how we can approach such a problem. First, we should be familiar with the equations of kinematics by now. Let's clear the question and write down the equations for the position in time and velocity in time of a moving object. Having written down the equations, let's now write down the initial information from the question. We'll write this down in a more mathematical way. For one ball, the ball written in blue, we have the initial position y sub 0 or y naught is equal to plus 1. The initial velocity is plus 10. This is the ball that's facing up. And gravity, which represents our acceleration, is approximately minus 10. We'll write down the initial information for the other ball in red. And the initial position is again plus 1 meter above the ground. And the initial velocity is minus 10 this time, because the magnitude is the same for both balls, but the directions are opposite. And of course, gravity is the same, it's minus 10. If we look now at our diagram or our animation, we see that we have two balls, one red and one blue, and we can refer to these when we look at the equations or the animation. The next thing to do is to plug in the initial information into the equations for each ball. We want to solve for the moment when each ball hits the ground. Let's start off with the blue ball and the blue equation, and we'll plug this into the position equation. So we have y parentheses t, the position in time, equals 1 for the initial position, plus 10 times t, v naught times t, minus 5 times t squared, where minus 5 comes from 1/2 times minus 10. We can also add next to our animation the moment when t equals 0 and the initial position, which is 1 meter above the ground. And then of course, as we let t run, as we let the numbers of t change, we should see the position change as well. Now we do the same thing for the red object. So we plug in the initial information into the position equation. We have y parentheses t equals 1 minus 10 times t minus 5 times t squared. It's almost the same, except the velocity has an opposite sign. We can also write down the initial position at time t equals 0 below the blue position. And as you can see, initially both balls start off at the same position. Let's run the animation and see what happens. We see that as the time increases, then the position of both objects changes. The blue ball goes up to some height, then stops and then falls back down, while the red ball only moves downwards. For example, at t equals 2.07 seconds, then the position of the red ball is minus 41.22 meters. That is, it's 41.22 meters below the ground. Of course, this is just a theoretical example, and we're only asked for the moment when the ball actually hits the ground. That is, when the position is equal to 0. If we run the animation again, we can see that the red ball almost immediately hits the ground. That is, it almost immediately is at a height of 0. Now the question asks us to find for both balls when they hit the ground and what their velocities will be when they hit the ground. We do that by finding what value of t gives us that the height or position is equal to 0. In other words, we plug in 0 into the position equation and solve for t. Starting off with the blue ball and the blue equation, we have that 0 equals 1 plus 10 times t minus 5 times t squared. Similarly, for the red object and the red equation, we have 0 equals 1 minus 10 times t minus 5 times t squared. These are two separate equations and two different times, one for the red object and one for the blue object. However, in both cases, we have one equation and one unknown. To solve for t, we can use the quadratic equation. The possible values are minus b plus or minus the square root of b squared minus 4ac, and all of that divided by 2 times a. Now, of course, in this example, as in other examples, there may be a simple solution, and you may not need to use the quadratic equation to find the values of your unknown. However, if the equation is not so simple, or if you want to be sure of your result, then you can always use the quadratic equation. Let's start off by solving for the blue equation. The parameters for our blue equation give us that a is equal to minus 5, b is equal to 10, and c is equal to 1. Remember, if our unknown is t, that is if we want to solve for t, then a will be the coefficient in front of the t squared terms, b will be the coefficient in front of the t term, and c will be the constant. When we plug this into the quadratic equation, we have minus 10 plus or minus the square root of 100 plus 20, where the 100 comes from b squared, which is just 10 squared, and then the plus 20 comes from minus 4 times a times c, which is minus 4 times 1 times minus 5, or minus negative 20, which is the same as plus 20. And all of that will be divided by 2 times a, or 2 times minus 5, which equals minus 10. When you enter these values into your calculator, you should find that the time is equal to 2.1 or minus 0.1. We have two results because one comes from the plus square root and the other comes from the minus square root. Now we have to decide which result to use. Since we're talking about time, then we're only going to use the time with the plus sign. We're not going to include the time with the minus sign because that doesn't make sense. The initial moment in time is t equals 0, meaning that any time before that is irrelevant. So the blue ball hits the ground at time t equals 2.1 seconds. Now let's find when the red ball hits the ground. We're going to use the quadratic equation, which will look more or less like it did before, except this time our b is minus 10, and so minus b will be plus 10. That is, the quadratic equation in red should look like plus 10 plus or minus the square root of 100 plus 20, and all of that divided by minus 10. Pay attention that in the square root we still have a plus 100 because even though b is minus 10, the b squared cancels the minus sign. When we solve for this equation, we get that t for the red ball equals plus 0.1 or minus 2.1. Once again, we can ignore the minus time, we can ignore the minus 2.1 that is, and so our result for the red object is that it hits the ground at 0.1 second. Let's draw a box around our results, and this tells us when each object hits the ground. The blue ball hits the ground at 2.1 seconds, and the red ball hits the ground at 0.1 second. The next question is what will be the ball's velocities when they hit the ground. In other words, what will be the velocities at the time that they hit the ground? Since we now know the time for each object when they hit the ground, then we can enter this into the velocity equation and find the velocity at that moment in time. Let's write out the equations for the velocity and time for both objects. The blue ball has the velocity equation 10 minus 10 times t, and the red ball has the velocity equation minus 10 minus 10 times t. Now we just plug in our previous results into both of these equations. For the blue ball, we have the velocity when the ball hits the ground, or the velocity when time t equals 2.1, is equal to 10 minus 10 times 2.1, which is equal to minus 11. The red ball hits the ground at time t equals 0.1, and so the velocity of the red ball at that time is equal to minus 10 times 0.1, which is also minus 11. Now we can see that both balls have the same velocity when they hit the ground, even though they hit the ground at different times. And the reason for this is pretty interesting. If we look at the initial moment in time, then we have two objects with the same initial position and the same magnitude of velocity, but opposite signs. The red ball is facing down, while the blue ball is facing up. The blue ball then begins moving with some initial velocity upwards, then stops and begins falling back downwards. At the moment when the blue ball reaches the same position as it started off at, that is, its initial position 1 meter above the ground, then it has the same initial velocity as it started off with, except in the opposite direction. So if the blue ball began with an initial velocity of 10 facing up, or plus 10, then once it passes its initial position as it falls down, it has a velocity of minus 10. Of course, this is the same velocity as the red ball, except it's at a different moment in time, and since both balls have the same initial velocity and feel the same acceleration, and of course start off at the same height, that means that they both hit the ground with the same velocity. From this information, we can also answer the question of how long it took for the blue ball to be thrown up, to stop and fall back down to its initial position of 1 meter above the ground. From the initial moment, it took 2.1 seconds until the blue ball hit the ground. Now the red ball was only in the air for 0.1 seconds. This tells us that when the blue ball was moving downwards and at the moment that it passed the height of 1 meter with a velocity of minus 10 meters per second, then it was also only 0.1 seconds until it hit the ground. In other words, from the moment when the blue ball left the height of 1 meter facing upwards until it reached the height of 1 meter facing downwards, then the time taken was the total time of the blue ball, 2.1 seconds, minus 0.1, or 2 seconds. In other words, it took 2 seconds for the blue ball to arrive back to its initial location. Then it took another 0.1 second for the blue ball to hit the ground. Let's look at the animation one more time, and we see that the red ball almost immediately hits the ground, and the blue ball takes another 2 seconds before it hits the ground. I hope everything was clear, and we can move on to the next question.